Hello everyone, welcome to this video. In this video, we shall be seeing Eisentien's criteria, which is used to detect the irreducibility of the polynomials, right, over the field of rational numbers. So this criteria has been given by the German mathematician named Eisentien in the 20th century, right? So before starting the proof and giving the statement, let us add some notation. So if you write A divides B, A vertical line B, that means you are talking about division. But when you write A, B with this vertical line tilted slightly, right, then you talk about fraction. So that means here I am saying A divides B and here I am saying A over B. So that means I write A over B like this, right? So there's a difference between these two. So be careful using the notations. So now let us come to the statement of Eisentien's criteria. What is that? It says that if you have a polynomial fx, say it is a0 plus a1x plus up to an x raised to power n, which belongs to zx, that means all the coefficients a0, a1 up to an, they are integers. Moreover, the degree of this polynomial is greater than or equal to 1. Then they are saying if there exists a prime number p such that all these conditions are satisfied, that means that prime number should divide all the coefficients of this polynomial except the an coefficient, right? Moreover, the p square should not divide the constant polynomial a0. If this happens, that means the given polynomials is irreducible over the given field Q. So let us look at the proof of this polynomial. We'll give the proof using the method of contradiction, which is the very famous method. What does we do in that? In that we assume that this fx is reducible over Q. That means we suppose the opposite. And we'll somehow get the contradiction proving, so that will prove that whatever we have assumed is wrong and fx is irreducible over Q. So let us assume fx is reducible, right? If fx is reducible, then we can write it as a product of two polynomials, say this and this. So now I'm saying the degree of this polynomial, first polynomial, this is R. So that means R should be less than n and BR should be non-zero. And the degree of the second polynomial, I'm saying this to be S. That means S should be less than n. And CS should be non-zero. Then only it is of degree S, right? And these all coefficients BI and CI, they are also integers. So this we have assumed. So now when you multiply these two polynomials, your first coefficient A0 would simply be B0 into C0, right? This one. This is obvious. And the last coefficient, that is the coefficient of x to the power n, that should be obtained by multiplying these two terms. So that would simply be BR and CS, right? So now the conditions that we are given is P divides A0. P divides A0 and P square does not divide A0. So what does this mean? If P divides A0, that means P divides B0 C0, because A0 is B0 C0. Now if a prime number divides the product of two numbers, B0 and C0, then P divides exactly one of those, right? P doesn't divide A0, right? Why this condition is important? Let us first look at this example that 5 divides 10. We all know 5 divides 10. That means I'm saying 5 divides 5 into 2. So that means 5 divides 5 and 5 does not divide 2, right? In the second condition is important because if I take an example like 5 divides 25. So in this case 5 divides 5 and because 25 could be written as 5 into 5, right? So 5 divides 5 and 5 also divides 5. So this condition is also quite important, because here both these conditions are given, so we have a case similar to this one. So 5 only divides one of these. So P only divides B naught or C naught. So let us assume without loss of generality, that means in both the cases we'll get the same results, right? So I have assumed this prime number P divides C naught, and at the same time it does not divide B naught, right? So this is one thing. Moreover, we are also given that, see the condition, that P does not divide the last coefficient an. So P doesn't divide an, that means what is an? BRCS. So P doesn't divide BRCS. And if a prime number does not divide the product of two numbers, that means they do not divide both the numbers at the same time. This is important, right? Suppose you have 2 and it does not divide 15, right? And what is 15? 2 does not divide 5 into 3. So that means 2 does not divide 5 and 2 does not divide 3 as well, right? So we obtain this thing. So now P does not divide CS. And what is this polynomial? CS was one of the coefficient from the second polynomial, right? Over here. So let us assume that let us assume there is another coefficient Cm where m is lesser than s, such that P does not divide Cm also, right? So this what should this coefficient look like? This Am should look like this, where the sum of these indices in every term is equal to m, right? So now, because of this condition, we have assumed that P does not divide Cm, so P does not divide this term. So overall, P does not divide the sum. That means P does not divide Am, right? This is quite obvious. So we say that because P does not divide Cm, it does not divide Am. So, but in our condition, it was given that P does not divide the last coefficient of fx. What was that? An. And now we are saying that it is Am. So that means this m should be equal to n, right? Just a second. So this m should be equal to n. So from here we get n is equal to m. And what was m? M was less than s. We have assumed it this way. And what was s? S was the degree of the second polynomial, which was less than n, because we assumed this to be a reducible polynomial. So this gives us n is less than n, which is not possible. You also know that. So here we obtain the contradiction. Similar is the case with this choice of division of P, right? Division of B naught by P and division of C naught not by P, right? So here, because n is not less than n in any condition, so we get a contradiction to whatever we have assumed. We have assumed fx is reducible, so that means it is not reducible, instead it is irreducible over the field of rational numbers. So this was the proof. This result is quite useful. Let us look at an example. They are given this polynomial x square minus 2. Now they are asking whether this is irreducible over Q or not. So here you can check because this is of degree 2, you can either apply that result that if you get any root for this in Q, this is irreducible. Obviously you get square root 2. Square root 2 is irrational number. It does not appear in this field of rational numbers. So you cannot find any root of this polynomial in Q. So therefore you cannot apply that result that we have discussed in the previous video. So let us try to use this result. Our polynomial is of this form. That means you can write this as minus 2 plus 0 times x plus 1 times x square. Now you have to look for some p such that all those conditions are satisfied. That means p should divide all the terms but the one with maximum power of x, right? And p square should not divide this constant term. So now we have clearly 2, right? P square does not divide this minus 2. P divide minus 2, P divide 0, and P does not divide 1. So clearly all the conditions are satisfied. Therefore, this polynomial is irreducible. It's quite simple as that. Let us look at one more example. If polynomial fx is given to be 3x raised to power 5 plus 15x raised to power 4 minus 20x raised to power 3 plus 10x plus 20, then you clearly see that these coefficients 10, minus 20, 15, they all are divisible by 5, right? Moreover, this is also divisible by 5, and if you take the square of 5, so that will be 25. So 25 does not divide 20. So we have this condition. Moreover, these conditions are fulfilled by 5, and 5 does not divide this coefficient 3, the one with the maximum power of x. So here p is equal to 5 satisfies all the condition of Eisentien's criteria. Therefore, the polynomial fx is irreducible, right? So now let us look at one corollary to the above theorem or result. So it shows the irreducibility of pth cyclotomic polynomial. Now what is cyclotomic polynomial? This is a special kind of polynomial, right? It is denoted by capital phi px, where p is the order of this polynomial, and this p is prime number, right? So it is defined like x to the power p minus 1 divided by x minus 1. And when you solve this, you will get something of this sort. So now we need to show that this is also an irreducible polynomial over Q. So we'll make use of Eisentien's criteria. So what we do is, we define some another polynomial gx, and what we do, we just replace this x, the x here in the cyclotomic polynomial, by x plus 1, right? So now if gx is irreducible, this implies phi px is also irreducible. Why this is so? Because this is some result that if you replace this x by, say, x plus 1 or x plus a in general, where a is any constant, the polynomial, whatever is the nature of this polynomial, that same nature this polynomial has, g of x plus a. If this is reducible, then this is also reducible, and if this one is irreducible, this one is also irreducible. So now we have constructed this polynomial g of x, which is basically phi p of x plus 1. So we just replace x with x plus 1 over here. So in the denominator you will just get x, and in the numerator you will have x plus 1 raised to power p minus 1. So let us expand this. So you can expand this like this, right? And this 1 and 1 cancels after expanding. So we have something like this. So you can divide this whole polynomial with x. So we'll obtain x raised to power p minus 1 plus pc1, x raised to power p minus 2, and so on, right? And what is pc1? It is simply p. What is pc2? It would be p minus 1 divided by 2, and so on. The last term p minus 1, the combination of all these is p, right? And p is the prime. So now you have this polynomial. Here you can see that in all these terms, second, third, fourth, and last, they all contain p. That means p divide this term, p divide this term, p divide this term also, right? So p divide every term this except the one with highest power of p. Moreover, p square does not divide this constant term. So, p being a prime number satisfied all the conditions of Eisentien's criteria. So, we can say that g of x, which basically was phi p x plus 1, so that polynomial is irreducible. That means this polynomial is also irreducible over Q. So I hope you understood all of these. That is it for this video. Thank you for watching.